Great. Hello, everyone. Happy Friday. Today we have our guest speaker, Dr. Yackar Mauzole. She works as a postdoctoral researcher in satellite oceanography at the NASA laboratory, JPL Caltech. In 2017, she obtained her PhD in oceanography at the University of Rhode Island. And during her PhD, she established global atlases of oceanic fronts that are persistent over time based on satellite observations. More recently, she worked on the dynamics of thermal fronts observed in the California current system, this time by combining sea surface temperature data to sea surface height data. While her work focuses on the physical aspects of fronts, these ubiquitous features are also important for fisheries and marine ecology, since they are known to be hotspots for biological activity and to impact the spatial distribution of nutrients across the ocean surface. As a woman of color in oceanography, one of Dr. Mauzole's goals is to encourage sociocultural diversity by helping underrepresented students navigate higher education in STEM and to have the same opportunities to flourish and be an integral part of the field as others. So if you guys have any questions for this presentation on clarification, feel free to ask during the presentation. But please hold all other questions until the end of the presentation. So Dr. Yackar, you are able to present.
Thank you.
Yeah, no problem.
I was saying just thank you for the kind introduction, and also that I am not anymore at JPL. And that's my fault for pointing you out to the wrong profile, but I am now at Scripps.
Okay, thank you.
But yes. And I'm gonna do it this way. So yes, the title of my talk is Applications of the FRODO algorithm to satellite observations and ocean simulations. As I said, I'm at Scripps right now. This is my second postdoc then. The first one was at JPL. And yes, I will just go ahead, oops, of course, and have a brief outline. For today, I will have a brief introduction to recap some concepts and just make sure that everybody is on board. And then I will explain some of my PhD work, where I developed the FRODO algorithm, some of my JPL work, and then finally, a little bit on my Scripps work, but not too much on that. So the core of my work is on front. And I don't know if everybody is familiar with fronts, but I'm sure everybody has watched at least one time in their life the Weather Channel. And sometimes they're like, there's a cold front going here, there's a warm front going there. Well, those are atmospheric fronts, and they also exist in the ocean, oceanic fronts. And fronts typically are defined as narrow boundaries between water masses or air masses that have different properties. And in the more specific case of sea surface temperature as a property, if water masses have different sea surface temperature, what you have then is called sea surface temperature fronts or thermal fronts, which is a larger term, a broader term. So you can see in the satellite image there, sea surface temperature, for the North Atlantic, part of the North Atlantic. Of course, the cold waters are in dark blue, purple, warmer waters are in orange, red. And every time you have a patch of color of water that is a different color, the line between them, the seam between them is called a front. So you can see already just in one picture like this that there are a lot of fronts. But the specific topic of my PhD was persistent sea surface temperature front. And so what is a persistent front? A persistent front occurs over time at the same location or more or less at the same location. So when I say over time, I mean over months, over seasons, over several weeks, but not just something that is very transient. So you may wonder, why are fronts important in the ocean? In the atmosphere, of course, again, Weather Channel, but why are fronts important? Why do I have to care about fronts? Why other people have to care about fronts? I always care. And so I gathered a few clips, of if you are in physical oceanography, of course, one thing is that ocean fronts are seen as vertical pipeline between the ocean interior and the ocean surface, and then above it, the the atmosphere. And so a lot of people are interested in the impact of fronts on the marine atmospheric boundary layers, but also if you are interested in air-sea interactions, air-sea exchanges, gas exchanges, working on fronts can be very useful. Oops. But then if you are in a different aspect of physical oceanography, if you're interested in ocean heat budget, ocean energy budget, fronts are also quite important. So I will just say that fronts can have any kind of scales. So if you think of the Gulf Stream is a planetary front. It is a front that is always there, even if it moves around. But you also have, let's say, fronts at all kinds of scales, even like smaller scales. So it goes from small scale, submesoscale, mesoscale, large scale, planetary scale. And that works for both spatial and temporal. And so if you want to consider the ocean energy budget, the ocean heat budget, then fronts are also an important part of the chain. Lastly, if you are not at all in physical oceanography, but you're thinking, well, maybe fronts can be important to me too. Well, yes, because like I said, fronts are vertical pipeline between the ocean interior and the ocean surface. A lot of time, vertical velocities are quite important at those fronts, and they tend to bring up to the surface a lot of nutrients. And so what would happen is that if you have a region in the ocean where you have a lot of fronts, like we'll call that a frontal zone, a frontal zone tend to collocate with a large marine ecosystem because you will have nutrients at the surface. So then you will have also more biological activity there. And for someone who is interested in marine ecology, that can be important. For someone who is interested in fisheries, that can also be important. So it's not a very narrow and obscure thing, but it can have an impact on a lot of different fronts. Okay, so then knowing what a front is now, we can go into my PhD research. So I work with Professor Peter Cornelian at the Graduate School of Oceanography at the University of Rhode Island. And for some context, you can see the date. I did my PhD in less than 3 years, but that's because I came to the grad school and then had a master first on a different topic, a different advisor, and then switched advisor and started working with Peter in fall 2014. And so what happened was that I had no idea what a front was, and I had never done satellite oceanography. So the first thing I did was going to the GSO library, trying to figure out a starting point. And the thing was that there was just one book on ocean front published in 1986. So at least that was a starting point, but it was not easy to find a lot of things to get started. And this map that you see here from Legekis is the first attempt to observe fronts globally. And he used that as when at that time satellite oceanography was still a budding field. Satellite oceanography really started in the 70s. And so he used the first observations that we had to map out large frontal zones. And you can see there are about 22 boxes. And for each box, he goes through all the fronts he can see and their properties and the processes attached to them. So this was the first attempt, right? And then the second attempt was led by a researcher named Igor Belkin, who works at URI. And what he did is he used the next generation of satellite and tried to draw by hand all of the fronts he could find. And so what he did, instead of having one global atlas, he had a collection of regional maps. And you can see all the red lines that he has drawn himself. So he would go through a lot of satellite data and by eye detect all of the fronts and map them out. And you can see all of them have a name. All of them have names, usually attached to their geography, and he knows all of the names. If you ever meet Igor and ask him about any front, he will tell you everything that he knows about each of them. So he has a great knowledge, but as I met Igor, I realized that there was a limitation to that because all of the maps were done by hand. And so it was harder to have reproducibility from that. Now, the motivation of my PhD lied on the fact that beyond those two major efforts to map out globally France, most of the studies on France are regional, meaning if I am, let's say, a GSO or UNH, I would be interested in New England, France. I would be interested in France in the Gulf of Maine. I would be interested maybe in France, like the Gulf Stream. And if I'm in California, I'm interested in coastal upwelling France. If I'm in Korea, I'm interested in the France in the Yellow Sea. And so every single group of research working on France would have their own criteria to say, this is a front, this is not a front. This is what we will take into account in our analysis. This is what we will discard. There was a lot of subjectivity and a lot of inconsistency between studies. And so I decided that, okay, let's just try to establish some consistency in that, and also to do that globally, you know? And so this is basically the bedrock of my PhD. I did a global study and I developed an automated detection method to reduce bias. And so what I did is that I used satellite observation. So Peter Cornelian is known as an expert in satellite oceanography and specifically in sea surface temperature. So we had, among other things, those three data sets, Pathfinder, FHR, MODIS Aqua, and MODIS Terra. Just as an aside, MODIS does not stop at 2011. It is still up in the sky, but I just wanted the times to be the same for all three data sets. And all three of those satellite data sets have SST fields that are daily. And when I say L3, that means they are gridded daily, and they have a spatial resolution at 4 kilometers. And the little picture here is just to show you what Pathfinder is supposed to look like. This is an illustration from NASA. I find it always interesting that you can actually picture what the satellite is. So I had several thousands of fields, right? But the trick goes that I do observe sea surface temperature fronts, but not from sea surface temperature maps. I do not use temperature as the input for my algorithm. I use something called frontal probability, which is the probability of finding fronts, basically. And the reason for that is that all three of those missions, MODIS Aqua, MODIS Terra, Pathfinder, FHR, rely on infrared sensors. And those infrared sensors are sensitive to cloud cover. And so what would happen is that if you do just things with temperature, you have a certain bias because sometimes it's cloudy. It's not that you have no front, it's just cloudy. And so we wanted to represent the probability of finding a front at a given pixel over time. And you can see the color bar goes up to 5. It really saturates around like 7% or something like this. So it's in percent. And it goes from 0 to 5. In the coastal region can go probably to 7 or 8%. And then, so why is it so low? To give you some context to that, this map that you see is 8,640 pixels by 2,882 pixels. So they are basically a lot of pixels. And if a front moves from one pixel to another, the probability at that given pixel does not increase. And so over 30 years, 92 to 2011, the probability of finding a front exactly at that specific pixel in the map is pretty low. And so that is why you see that, oh, okay, it goes from 0 to 5%. And that doesn't show you temperature at all. It just shows you the likelihood to observe the fronts, right? And that will be the input from my work. Now, what you can also do is apply the same thing for climatological seasons. And I would recommend you focus on one area, like let's say the Gulf of Maine or around the Labrador region or the Gulf of Mexico. And you can see how it changes over the season. So when I say climatological season, I mean I had 30 years worth of winter, 30 years worth of spring, summer and fall. So when you aggregate them, you get those frontal polarity. And you can see there is some change, and it's also a little bit different from the long-term frontal probability. Now, how does FRODO work? How does the FRODO algorithm work? So FRODO again means frontal detection in the ocean. And I came up with that name not so long ago, pretty proud of this. So the principle of the algorithm is very simple. What you do is you scan vertically and horizontally your frontal probability map. Just as if you are passing your hand on something that has some 3D relief and you're trying to figure out all of the bumps, all of the local maximum. And so the red arrow shows you the profile then on the right-hand side. Again, some context, this is Australia, hence the negative latitude. And so you have the land all the way to 34 degrees south. And then you have a sharp peak. And then you have smaller peaks following that, right? So when it's land, of course, we have no frontal probability. But then in the ocean, the frontal probability is very rarely zero. It tends to be non-zero, but quite low, around 1 or 2%. But then if you have a persistent front, what can happen is that you get a sharper peak. And what do we do actually if you scan the image like this, from top to bottom and left to right, what do you get? You get something like this. And you can see here a lot of noise. You can see the front, but also a lot of noise. And so even if the principle of the algorithm is very straightforward, the core of the effort lied in reducing the noise and singling out the front globally, right? So I'm just going to show you how you can get there from this to this, from this, and then finally this, where you can isolate the features that are of interest to you, right? And how you can do that, there are several ways, but one way that is pretty efficient is called the peak selection. And so going back to the image when you scan from top to bottom, this image from South Australia, you can check that, okay, if it's a persistent front, then most likely the height is a bit more and the peaks are narrower and taller. But if it's not a persistent signal, then it's broader and shallower. And so by saying, I want to keep all the peaks that have a certain height and all the peaks that have a certain width, both conditions at the same time, you get something like this, where only this peak remains and everything else get discarded. So that's one way of reducing the noise. That's not the only way. And the tricky part comes to, this has to work globally. It shouldn't just work for one front. This has to work globally. Because once you apply that criteria, you don't change it from one region to another. It's the same criteria everywhere, right? And so what do we get if we finally get this done, noise reduction and everything? We get something like this. And so this is one of the global maps that I got from my PhD. Again, the background here is still the frontal probability, the one I showed you before, the input, and the red lines are the output, right? And so you can see it's covered in fronts. It's not random, but it's covered with front, and it seems sometimes quite overwhelming. You see a lot of fronts in the Southern Ocean. You see a lot of fronts due to the Gulf Stream extension and the Kuroshio extension, and then more also in the coastal upwelling systems, like in the Bengala one over here, the Canary one. There is also here with the Peru Chile. So you can see a lot of fronts everywhere, right? And it can be pretty overwhelming. Now, if we look at the climatological seasons, I would recommend again to focus on one region of your choice and check it. So this is fall, starting by fall, of course. This will be winter. This will be now spring. And then summer, right? And so you can see that there is some variability depending on the seasons, even if the fronts are persistent, because a persistent front doesn't mean it's a permanent front or a steady front. Those are different notions. And so it looks like, oh my gosh, so many fronts, so much information in that. But you can also look just in one region, and then it's way less overwhelming suddenly, and you can make sense out of it. And so this is the east side of the US. And in the case of course, New England and Southeast US, the fronts have been already documented for many, many years. And so for me, at least, that's a good thing that I can find through my method the fronts that have already been discussed in the existing literature. So this was reassuring on that side. The other thing that was interesting is that for some of those fronts, there was a higher degree of details that was achieved because this data set is 4 kilometer resolution, when at the time of Belkin's study, it was 9 kilometer resolution. So I got more details than what he had done, simply because my data set had a higher resolution. The white line for the white lines are the isobars, if you are interested in knowing that. And in particular, what we saw is fronts that you can see with your naked eye, which is not always the case. But this time you can see them with your naked eyes. So this is a satellite image of the Bahamas and the Florida Keys. The contrast in color, in visible color, is due to a contrast in depth from shallow water, shallow coastal waters, and deeper ocean water. And so you can see those fronts because shallow coastal waters don't have the same properties and the same temperature as deeper ocean waters. So you can clearly see even close to the Florida Keys, or even closer to the island here, that the waters are different. And the good thing for me is to say, okay, the fronts that were documented previously, like the New England fronts, I found them too. So that's good. That's the first check. But there are also fronts that were not detected before, and that we can detect now through my method. And I can see them, all of them here, along the Florida Keys and between the Bahama Island, and also between all of those islands as well. I can detect all of those fronts now. And so bias was reduced in this study because you impose one criteria globally to detect fronts and not region by region. And there were 5 global data sets of persistent fronts that were obtained. One for the long-term mean, 1982 to 2011, and then the climatological seasons. I just showed you the locations of the fronts that were detected, but I also have the priorities attached to the fronts. And where it was really interesting for us is that in regions that are under-documented, especially in the Southern Hemisphere, you could also see all of those fronts, not just the fronts that we know around the US or Western Europe, but anywhere. So that was pretty interesting. Now, my postdoctoral research, I had an appointment for 2 years at JPL, and I will just explain a bit what was going on. So, like I said, Peter Cornelian is an expert in satellite oceanography and an expert in sea surface temperature. And to me, one of my goals was to become proficient in more satellite variables. So I joined JPL to work with Dr. Li-Weng Fu, who is a specialist in altimetry. He is the current project scientist for the SWOT mission, which is the new generation altimetry from NASA, but also he has been part of the TOPEX mission, the JSON mission, Poseidon, and everything. So he is an expert in altimetry, and I wanted to learn more about this. Right? So this time, like I said in the outline, this is a regional study. And we focused on the California current system because JPL is located in California. So the California current system, which should not be confused with the California coastal upwelling system, is a much larger domain, and it extends from 50 north to 20 north. So it is pretty large, and most people would divide that into 3 different subdomains. So you have the northern CCS, you have the central CCS, and then you have the southern CCS. And in this talk, I will mostly talk about the central and southern CCS. Now, another notion, I'm pretty sure most people would be familiar with it, but just in case, coastal upwelling is the main process observed in the California current system. And this is when you have wind blowing along the coast and the waters at the surface are being displaced offshore because Earth's rotation, and then they're being replaced by deeper waters that are cooler and richer in nutrients. So this is what you observe mostly if you focus on surface ocean processes in that region. Now, when I got started there, I wasn't sure at first, I didn't have a defined project when I arrived. So the first thing I did is I combined the fronts that we had collected with Peter, and then I placed them on top of altimetry data. And so this time series shows you from 1993, when altimetry records started, to 2011, when my personal SST fronts record ended. The time series are the evolution of what was happening, right? And so I was just trying to get an idea, a better sense of what was happening in the region. And one thing that we stumbled upon was the fact that sometimes fronts were behaving a bit strangely. So this panel is from the paper we published this year. Panel A is July, B, August, C, September, D, D, October. What did I say? July, August, September, October. And the color field is a sea level anomaly, average for the months. And the black dots is the location of the fronts over that particular month, right? And typically what you would expect is that the fronts are matching the contours of the mesoscalides and the geostrophy, the surface geostrophy. And that's what you see mostly in A and B and C in the central part. But then in D, and also a little bit already in C, what you see is a lot of fronts. You see a lot of fronts in October. This is 2008. And those fronts do not respect the geostrophic contour. They're all over the geostrophic contours. And this phenomena happen often enough that I picked up on it. It was just a one-time thing over the 20 years that I had of data. It happened. It wasn't every year, but it was often enough that, oh, what is this thing? What is this thing? And I went to a few experts on the region and asked, do you know why this is happening? Can you explain why this is happening? And they had no answer, right? And so that became the motivation of my work at JPL, because you have to remember, I came from a global study, so I had no idea of what exactly was going on in the California current system besides what I was reading. And what I was reading is that coastal upwelling is the major defining process in the region, and it occurs from spring to fall, and mostly in northern and central CCS. So my question then was, why am I seeing fronts, so many fronts, in the southern CCS and in fall? It's, for me, if I think of coastal upwelling as a box, then temporally, this is later than coastal upwelling, and then spatially, it is south of the main region of coastal upwelling. So it's outside, and then outside again of the coastal upwelling context. And I was thinking, but why am I seeing all those fronts? Because by default, people would assume that if you see SST fronts in the region, they are associated with coastal upwelling, but it didn't seem like that was the case. And so we went from the satellite observations to the ocean simulations. And so at JPL, there are a few people who are very proficient and fluent at using the MIT GCM, which is one of the ocean models you can get access to. And that particular simulation was performed at 1/48th of a degree, which basically means 2 kilometers. So 2 kilometers, again, this is twice smaller than my satellite data from my PhD. This is very high resolution. And the first thing I did once I got access to the data from the model is that I wanted to have what I called a sanity check. I just wanted to make sure that the model was doing the right thing, because I had never used that model previously. So what I did, if you see this panel, A and B are the Argo data, the Argo Institute data, and C and D are the model. And so you can see the difference of resolution. This is fine. What I wanted to check was whether the large-scale features were well reproduced by the model. And so A and C are for July. This is the monthly average SST. And B and D are for October. A and C are for July because July is assumed across the literature to be the peak of the coastal upwelling season. And B and D are for October because that is assumed to be the end of the upwelling season. All right, so I wanted to check for those crucial times, does it look okay? Can I go ahead using that model? And it did, fortunately. So what I did this time is adapt and apply then the FRODO algorithm to the simulations. My goal was trying to detect the SS difference in the simulation. And you can see A and B, again, July, October, those are daily fields this time. And you can see patches of cold water. Let's just be mindful, the color bar goes all the way down to 10 degrees Celsius. So maybe it's, what, 45 Fahrenheit? Sorry. But basically, you know, I was successful in detecting fronts in the simulation. And you can see this, the central CCS is the classical case, the coastal upwelling case. This looked great. I was satisfied with this. Now looking into southern CCS, it's the same day. I'm just moving my cursor across the map. It's interesting because we see a lot of fronts, but there is no major coastal upwelling here. There is a little bit if you check close to 28 to 30 degrees north, a little bit, but there is no large patch of cold water that is being upwelled in the region, yet you see so many fronts. And so this was kind of the first clue that, okay, something is different. The dynamics in the region may be different here. Now, the second thing that we did in this study was looking at density gradient. And why did we do that? So for people interested in frontal dynamics, they tend to look often at density gradients because density is a function of temperature, pressure, and salinity. But if you are at the same level, then it's only temperature and salinity. So usually if you see something in temperature, you would expect it to exist also in density and vice versa. But this time, you know, plotting the density gradient in white. So you can see this is July 15 and again, July 15, same day, but in the central CCS and the southern CCS, you can see that the density gradients in white are matching pretty well the temperature gradient, in the case of coastal upwelling, which is kind of normal and expected because when you upweld cooler water, then yes, you have a contrast in temperature, but also a contrast in density. So this is not surprising. We see density gradients align with temperature gradients. That makes sense. But now in the southern CCS, we see much less white. You still see some, but not all the fronts are associated with density gradients. And so this is already our second clue now that something is off. Now, the last clue I will present today, not the entire last one, but the last one I will present today, are vertical velocities. So this panel shows you the color fields are vertical velocities. And you can check. It's from -20 to +20 in meter per day, because upwelling fronts are characterized by large vertical velocities. And that has been also measured in situ. You know, it's not just the simulation making it look so dramatic, but it does goes from 10 to 20 meters per day. And so you can see the black dots in those maps represent the location of the fronts where the vertical velocity is above 5 meters per day in absolute value. The reason why I plotted it this way was for me to see if the fronts I was detecting were having strong vertical velocity like you would expect. And so again, A and C are for July. And in A, I see quite a number of SST fronts with strong vertical velocities, quite a number of black dots. Then in October, I still see quite a few fronts with large vertical velocities. But then regardless of the season of Baja California, first of all, the color field is much weaker. So you can see that there are no strong vertical velocities almost. But also, you don't have that many fronts associated with strong vertical velocities. And so this is our third clue now. The assumption that we brought to explain what we were seeing is called thermohaline compensation. So like I said, density is a function of temperature, density, pressure, and salinity. If you are at the same depth or level, then pressure is a non-issue, and then you have just temperature and salinity. And as I'm sure you know, they have opposite effects on density. So they can actually compensate each other. And what they do is they don't cancel density, but they cancel density variation, aka density gradients. So you may see a temperature front and may not see a density front because of this phenomenon. Now, what we introduced in our study was what we call the compensation index. And it's a measure of the relative importance of temperature gradient to density gradient. And if it's much larger than 1, it means you have strong compensation. If it's close to 1, that means both gradients have relatively close magnitude. And so you can see we plotted the compensation index across the CCS, and we selected 3 subregions. The subregion 1 is still the central CCS, coastal upwelling, classical case, well documented. And then 2 and 3 are of Baja California and in the region when we're not sure what is going on. And so one important takeaway from that study was that thermohaline compensation is not a binary process. It's not like an on-off switch. It is over a spectrum. So it is not either it's compensated or not compensated, but it's over like it can be not compensated, partially compensated, or fully compensated. And so I can show you now. You can see the white little sections. If you take the vertical section, this looks like a textbook. You have strong vertical velocities. So the color field is the vertical velocity, sorry. So you have strong vertical velocities. The red lines are isopycnal density contours. And the black lines are temperature contour, isotherms. And you can see that the black lines, the red lines are well aligned, and that they outcrop where you have the fronts. So far, everything is good. But if you move to the partial compensation case, the vertical velocities are much weaker. You have still isopycnals, but they are misaligned, they are tilted compared to the isotherms. And so you do see a temperature front, but you may or may not see a density front at that place. And then fully compensated, no density variation. No isopycnal, no density variation, very close to zero, or I think at most, if I look at the color bar, at most 3 meters per day in terms of vertical velocities, so much weaker than 20 or 10. And so you can see that you see a front, but then you can be sure you won't see a density gradient associated to it. And so in summary, not all of the fronts, but some of them in the southern CCS are associated with processes that are distinct from coastal upwelling, which is observed in the northern and central CCS. And through using high resolution simulation, we could check that, okay, their vertical velocity is much weaker. They don't always have a density gradient attached to them. And there were some more things that I didn't go over today, but several clues regarding frontal dynamics showed us that the fronts that we saw initially disrespecting the geostrophic contours, those fronts are like that because they are passive, they are compensated fronts, and they are not active fronts. They don't have the active role that the ones in the central CCS may have. In the southern CCS, because you may have thermohaline compensation, what happens is that you see fronts, but those fronts don't have an active role, and they are just being advected by the background flow. And one of the implications of that is if you are studying marine ecology, fisheries, and things like this, knowing that you see a lot of fronts, but those fronts don't have vertical velocities attached to them that would bring up to the surface nutrients, this is important to know that not all the fronts are equal, basically. And so that was an application of the algorithm I developed during my PhD to simulations. Now, my current work, which I started last year, is with Professor Jen McKinnon at Scripps. And Jen is part of the MISO-BOB mission. The MISO-BOB is, Bob is the Bay of Bengal. So the MISO-BOB, how do you call that, initiative is about studying the Bay of Bengal and ocean processes there. And so Jen went on a cruise in summer of 2019 before I joined. And this is an illustration from their cruise report where they show, okay, we had the altimetry here, and this is the path of our ship, and we saw a filament. And they were like, oh, we saw a filament, we measured temperature variations and density variations and things like that. And the origins of the filaments were not fully explained. The question of whether that was the only filament in the region, we didn't know. And was that something that was recurrent, or was that just a one-time thing or random thing going on there? So those are the major questions that I'm interested in, looking at what we've done during that cruise. And so again, I'm starting with just the basic stuff. So for me, I just moved from JPL to Scripps. I know more about altimetry. I plot the altimetry time series during the cruise time. And for me, it's just a way of getting a bigger picture of what was happening, right? And so I can see, oh, okay, you have mesoscale eddies. So the blue and red here. And I see their cruise was over here. So like, oh, okay, I see. This is kind of the context of your cruise. And so going back to my PhD work, you can see the red lines on the left-hand side picture. The red lines correspond to the persistent sea-surface temperature front that I detect in the region, which in that particular region is fully aligned with the local bathymetry. So this is a shelf, what we call a shelf break front. And Again, I plotted it in black in the right-hand picture. And so one thing that I understood is that coastal waters in the region are confined in an urban near the coast, near the Indian coast, and that the persistent front also blocks the cross-shelf transport, right? So you can't just have coastal waters along Indian coast and then flowing into the Bay of Bengal. That's not what happens, because you have the persistent front, the shelf, and so you have transport being inhibited. But my assumption is that there are specific locations marked by the black stars where you can facilitate cross-shelf transport due to the eddies. And so CE means cyclonic eddy, AE means anti-cyclonic eddy, basically. And so I was trying to this time combine my knowledge of SST and altimetry and trying to see if, okay, can I also see what they see from a cruise from space? And so you can see the average altimetry map for the time of the cruise. And you can see I use, so FSLE, I won't go into the details. I won't bore you with that. But FSLE is basically a derived product of altimetry that allows you to see finer structures in the altimetry field. And so you can see from the Lyapunov exponent FSLE that there's a patch of coastal water around 1718 north, the white patch that is being steered by the eddies and being how would you say, thinned out into a filament, right? And this filament is flanked by two strong fronts. If I look now at the daily SST from Moody's, I see cold water. If you see a lot of gray in the ocean, that is the cloud cover during monsoon. This has been a recurring issue for me. And so the last thing I will show you today is that I tried to apply the FRODO algorithm that I had developed during my PhD to sea surface salinity fields, because the Bay of Bengal is salinity dominated, and there's a lot to understand and to do about salinity in the region. And so I was trying just to see, would the code also work if it's not sea surface temperature? And it seems to work, but one thing to understand is that sea surface salinity as a product is 10 times coarser than sea surface temperature, at least the sea surface temperature I was using. So again, the sea surface temperature fields I was using were about 4 kilometers spatial resolution, and the sea surface salinity is about 40 kilometers. So you don't see the same degree of detail, but the algorithm seems to work and detect fronts, especially because you have river runoff going on, and so you would have strong fronts of salinity that we know exist. So this was an ongoing thing. And then regarding the chlorophyll, I haven't tried this time to apply my algorithm to that region specifically, especially because the cloud cover is so important during certain months because of the monsoon. And so I always get very, how would I say, incomplete fields. And it's really hard to then apply the algorithm to detect fronts in chlorophyll, but I'm not giving up. And so with that, I believe I can say thank you. I also just want to give a small shout out to my friend Annie, who was the one who invited me for this talk. And I realized, I think yesterday, that it's been 10 years since we've known each other. So really happy about that. And yeah, if you have any questions, if I got you lost somewhere, let me know. If you want to know more details about anything, I'm also here for that.
Provided you can hear me. It struck me that you're trying to detect fronts, your features, and yet you're doing that by analyzing isolated pixels, which are point features. And so it seems to me that there's a conflict between what you're trying to detect, which is a line, and the way that you're doing the analysis. And I think your analysis is good. I really like what you did. But if you could convert the pixels into vectors, spatial vectors, then there are statistics like categorical wombling that allow you to determine if two lines are the same, or if two sets of lines are the same, so that if you have a set of fronts for this August and a set of fronts for next August, you can determine, are they perpendicular to each other? Are they the same as each other? So I'm just curious, with what you did with the analysis with the pixels, did you consider extending that so that you could put lines together, like your picture here on the right? That clearly looks like a line, but I assume it's made up of individual pixels. It's not actually a vector structure that says X to Y, XY to XY to XY. It's isolated pixels. Could you just comment on that?
Sure. So it's a great question. I did not explain that beyond the noise reduction, there was some efforts done to actually connect the pixel into objects. And so that also took some time because, like you said, sometimes if two fronts are too close or things like that happen, or if the noise is not completely cleared out. But the final product is actually a line. And so you would get lines at the end of this. And another thing that we get is you can get the envelope, the contour of the front. So if we look at the front at 36, 35 degrees south, I get the line that is actually at the local maximum, but also I get the edges because after I finally get the cleaned up pixel, I get that into a line, and that took some time because it's global. So the code broke a lot of time, but you get a line, and then from the line, you can go back and try to get the contours of it, and then also the properties, not just average over the segment, but within the envelope of the front, right? And so, yeah, I did not show that step because it's less glamorous than I would like, but yes.
Yeah. Thank you. And it made me wonder that when you're looking at fronts, of course, it's not just the location, but it's also the length. So if you have, in one year, a dashed line, and then in another year, you have a continuous line, you can potentially say, oh, well, it's not the same because, they're broken up. So anyway, thank you very much.
Oh, sure.
Anyone else? You may raise your hands or ask questions or unmute.
I believe there's a question on the chat from
Oh,
John
yeah,
Kelly.
John Kelly. Okay. Yeah, you just spoke up. Have you applied or plan to apply your font identification technique to SST forecast guidance from NOAA, NWS Global? So many acronyms, man.
Wait, can I also see the question? I need to see the question too. Okay. Oh, I see. Okay.
Yeah.
Conversely.
Global RTO. I'm not sure what that is. RTO, FS, and or NOAA, NOS, operational oceanographic forecast systems, e.g. Northern Gulf of Mexico.
No, I haven't tried. So the short answer is I haven't tried applying that identification technique. Like I said at the beginning, so the core technique, the original technique, is for persistent SST fronts. So it works better if you have long-term time series. If you want to just locate fronts on daily fields, the original code from Caillou Cornillon, a previous student of Peter, would work just fine if you want to detect fronts on a daily basis. But if you want to detect them on a longer time scale, then my algorithm might be more useful. So I don't think I have, well, I have applied that globally. So I have my frontal data in the Gulf of Mexico, but I haven't applied that to those specific data sets. And I don't know if you could specify whether they have like what's their spatial resolution or anything like this. But it should work. The modified version of the FRODO algorithm should work because it does work on salinity daily field. It has worked on chlorophyll daily field. I haven't showed it here, but I have tried that in the Mediterranean Sea. But I don't know, you have to be kind of mindful of what it is that you're trying to see. And the Gulf of Mexico has a small issue, which is that in summer, it's harder to detect sea surface temperature fronts because it gets so warm. So I wouldn't know if the code won't break, but I don't know if you will see what you want there. That would be my answer. Sure.
Okay. John Kelly say thank you. Tracy Mendel say great talk and thank you. And Sally Jarmus is saying wonderful presentation and thank you as well. Are there any other questions or? Okay, so we will be finishing by that, and thank you so much, Yackar, for coming today and giving your talk. And everyone have a wonderful weekend.
Thank you. Bye, everyone.
Bye.